In the previous movies, we looked at how to use the t-test to compare the means of either two different groups or the means of the one group over 2 points in time. In this movie, we're going to look at the one-way analysis of variance, or one-factor ANOVA, also an extremely common measure in inferential statistics. Like we did with the paired t-test, we're going to use some randomly generated data for this exercise. What I'm going to do is I'm going to create 4 variables, x1 through x4, and each one of them will be sampled at random from a normal distribution. That's the R-norm function. I'm going to get 30 cases for each, and I'm specifying the means as 40, 41, and then 2 at 45. And then the standard deviation is going to be 8 all the way across. And so there are differences, but they're small. Now, I should mention that if you actually calculated the one-way analysis of variance using these summary values, which you can do, you would get this result. An F of 3 and 116 degrees of freedom is equal to 3.24 and a probability value of 0.025. By formula, these groups are statistically significantly different. The question is whether it will show up that way when we're actually generating random data from each one. So let me get these 4 variables. I'm going to do them all like that. So now I have the data, and I'm going to get a box plot that looks at the 4, just side-by-side box plots. Now, what's interesting about this is you can actually tell that right now, even though group 1, x1, is supposed to have a lower value than 2, it's flipped around in terms of the median, and they all look really similar. In fact, what I'm going to do right now is I'm going to do this a few more times, and I'm going to run this command. And by doing that, it's going to generate these variables over again and draw a new box plot. So it's going to be different every time. I've got those all highlighted. I'm going to do Command Return. And then I'm going to do Shift Command P to just do it over again. And you can see how it bounces around according to these random variations. And sometimes it's contrary to what you would actually expect. I'm just going to stay right here because this pattern seems basically consistent with what we want. I'm going to clear out the console because right now it's full of a lot of code from doing this every time. So I'm going to do Control-L to clear the console. Now, boxplot is not the same thing as actually doing an inferential test, in part because it shows the entire distribution, and the inferential test is based on the means and the standard errors. Plus, obviously, this is a graphical and not a numerical analysis. So what I'm going to do right now is I'm going to take my 4 different variables, x1 through x4, and I'm going to combine them into a single data frame. The way I'm going to do this is I'm going to create a data frame called xdf, that's for x data frame, and I'm using the function data frame because I want it to be a data frame. And then I'm also using the function cbind, that's for column bind, which means I'm going to take these 4 columns, stick them together, declare it a data frame, and save it as xdf. So I'm going to do that right here. And in fact, if I just click on this now, there you can see it in sort of a spreadsheet format, x1 through 4, and I've got my values for each one. All right, good deal. Let's get some summary statistics for that. And if I scroll up here, you can see the minimum, the quartiles. Let's look at the mean for each one. We have 38.4, 41.65, 45.42, and 46.04. So those are actually pretty close to the means that I specified in the random normal function. All right, now what I'm going to do is, because these are in 4 different columns for the one-way analysis of variance, it would be better to have them in a single column with all the values in one column and then another column that indicates their group membership. I'm going to use the stack function, where I take the data frame and I stack it, and I'm going to put it into XS for X stacked. So I'm going to do that right here. And now you see I have 120 observations of 2 variables. Let's click on that. And that is the more conventional layout of rows and columns for a one-way analysis of variance. From there, I can conduct the actual analysis of variance. By the way, you can pronounce it ANOVA or ANOVA. It doesn't matter to me. I'm going to use this one. I'm going to actually do the test, which in R, the function is AOV for analysis of variance. And the way you specify it is by saying, what is the outcome variable? Here is called values. Let's go back to this X stacked. You see right here, this variable, the outcome variable, is called values. And this one that has the group membership is called ind, for like independent variable. So I want to analyze values as a function of ind. That's what the tilde means. And the data set is XS. And then I'm going to take all of that and I'm going to feed it into an object called ANOVA1 or ANOVA1. And the reason I'm doing that is I would be able to get the results by just running the function, but by saving it, I can get some extra summary statistics about it. So that's a helpful thing. So I'm going to run that one right now. And here's what we would get if we didn't save it but just ran it on its own. We would get this table. It tells us the call, what the actual formula was that we used, and we get the sum of squares, and we get the degrees of freedom. And while that's all important, it's not usually what we're looking for. The more specific information that we want about the hypothesis testing is going to be under summary. So this is why I saved it as an object, because then I can call summary here. I'm going to click that, and now I have my little analysis of variance table. It gives me the degrees of freedom, the sum of squares, the mean squares, the value of f, and the probability of f being greater than a particular value. That's the actual probability value. And so what I'm looking at here is degrees of freedom of 3 and 16, and then value of f of 5.779, which has a p-value of 0.001. That is much lower than the conventional standard of 0.05. And so this is a statistically significant finding. Now, let me just compare it to the formula finding we had up here. And that is, if I just took the numbers here and ran them through, I'd get a value of f of 3.24. That's right here. Whereas with my data here that was randomly generated, although I stopped when it looked like a nice pattern, was 5.779, and the p-value was much lower. The 0.001 as opposed to the 0.25, although both are statistically significant. Come back down to the bottom here. Now, when you're doing a one-way analysis of variance, you get a significant finding. It tells you that there are differences between the means somewhere in there, but it does not say where the differences are. And so at this point, it's common to do a post hoc or after the fact comparison. There's a lot of choices here. A lot of people do the Scheffé or the Bonferroni, but I don't like those tests very much because I find they tend to be overly conservative. I'm a fan of the Tukey. John Tukey's honestly significant different test, in part because of the layout it gives. So I'm going to do the Tukey HSD. That's the name of the function. And I'm going to run it on my object ANOVA 1. That's the results of the test. So I run that, and I actually get a lot of printout here. What it's doing is it's comparing every one of these groups. This is x2 to x1, x3 to x1, and so on and so forth. What we can do really easily over here is we can just look at these two, or we can just look at these p-values here on the end. We have an observed difference, a confidence interval for the difference, and then we have a p-value. And interestingly, only 2 of them are statistically significant. And what it is 1 versus 3 and 1 versus 4. None of the other effects are different. 1 and 2 are the same, 3 and 4 are the same, and 2 and 3 and 2 and 4 are the same. So we can tell that group 1 on the left is lower than groups 3 or 4, but there are no other significant differences. Now, depending on which post hoc test you're most comfortable with, there are a lot of other choices. Let me just mention, this is pairwise t-test. Those are a collection of post hoc tests. I'm going to scroll down here for a moment. There are a lot of different ways to do this. And also, p-adjust gets you specific methods. So there's your Bonferroni if that's what you want. Anyhow, that's the basic principle of how the one-way analysis of variance works. A very common test in research, and one of the nice things that gives you a lot of flexibility and options in R. I encourage you to take some time to look at the options, especially to see about the kind of graphics that you can produce with this and the post hoc comparisons. And I'm sure you'll find exactly what you need for your own purposes.